The main focus of this tutorial is frequency and buckling analysis using linear eigenvalue techniques. However, there is the opportunity for the frequency problem also to show you something using dynamic analysis methods that are available in FreeCAD and Calculix. So I've also taken that opportunity here to show that. I'll go through some description of the problems first of all and some background theory before moving on to the main part of the tutorial in using the codes. Then I'll do the frequency tutorial. For this I've selected a tuning fork. It's an example I use in the book. It allows me to show you a little bit more of the CAD capabilities in FreeCAD. Then I'll move on and do a linear eigenvalue frequency analysis of this tuning fork and follow that with a dynamic analysis of the part using implicit direct integration, and can show you that we can get the same sort of frequency behavior as we can with a linear eigenvalue analysis. Finally, then I'll move on to the buckling part of the tutorial, which uses a thin-walled box section loaded like a cantilever beam. One end of it is built in and the other end is loaded. I'll show you quickly how to build the CAD model, and then we'll do the linear eigenvalue analysis. There's an example here at the top just to give you an idea of what this linear eigenvalue analysis can do. It's for frequency problem. It's a very simplified tuning fork that I use in the book. Basically a set of cubes that have been modified and joined together to give you this simplified representation of a tuning fork. We have 4 modes there I've shown. The first mode is oscillating to and fro this way. The second mode is very much the same actually as the first mode, and you can see that actually by the same sort of frequency behavior. I'll come to that in a moment. This one is oscillating, this arm is moving this way and this arm is moving that way in an oscillatory motion. That would be the third mode here. And the fourth mode, which is the main mode of a tuning fork, has each of the arms moving opposite to each other, this way and this way. These are the sorts of results you will get from a Calculix eigenvalue analysis, and also this information is provided. These are the eigenvalues, so-called eigenvalues, which I'll show in a second. The omega squared values. These are the omega values for rotational frequency, and here are the actual frequency values, which is the number of cycles per unit time, so typically hertz. For these analyses, you start off using the dynamic equations of motions. We ignore damping in these types of problems, so you're left just with this equation. You then assume that the nodes are moving harmonically. That means that each of the nodes has to be moving in some sensible motion compared to the attached nodes. So this is our relationship that we assume. This is a displacement, a relative displacement of the 2 nodes, which is to be determined. And this will be the frequency, the rotational frequency of that the nodes are moving. You will assume that for any particular mode, all of the nodes are moving with the same frequency, rotational velocity, and this is time. So if we can determine this and we know the rotational velocity, then we can get our displacements. This, I have to emphasize, this is only relative displacements of the nodes. It's not actual displacements of the nodes. The technique doesn't apply any loading. We don't actually know the magnitude of the displacements that occur. And so, since this is relative displacement of the nodes, then this is also only relative displacements. But this is changing with our rotational velocity. From this relationship, if you double differentiate, you get this relationship. And then feeding both of these into here gives us this governing equation for the system, set of equations for the system. Now there's two possibilities. Either your displacements are zero, or we have to find values of this which are zero. This would be trivial, so we just take this, and the condition for this to be zero is that the determinant of this is equal to zero. So we have this relationship here, and I've just expanded it for a typical system, which is given here. What we have then is, if we've got n degrees of freedom, we will have n values of these omega squares. These omega squared would be the eigenvalues. There will be n values of these, and for those n values you will have n values of possible displacements. These would be the eigenmodes, and these are the eigenvalues. Hopefully this will make a little bit more sense on the next slide. If that's not clear, we'll try and look at this a little bit closer with an example on the next slide. This just tries to put a few numbers, if you like, to the previous expressions on the previous slide. I'm considering just two very simple springs. They're shown up here. They're in series. There's three nodes, 1, 2, and 3. So the first spring is denoted K12, second spring K23. There are masses attached to the nodes. These masses could be the masses from the springs themselves, but you could also attach a mass to each of these nodes. And each of these nodes will be moving harmonically as I've depicted there. The first one will have a harmonic mode shape, D23, and it will have a angular frequency omega 2. Same sort of thing for node 3. The stiffness of this system is the standard stiffness. It's given here. I've assembled the stiffness matrices together, so we've got K12, K minus K12, minus K12, K12, and the same sort of thing for K23. The dynamic equation of motion, taking into account the constraints for harmonic motion, is then given by this expression here. So we've got these squares of the angular frequency, the masses of the nodes, and the stiffnesses here. Because node 1 is constrained, we can introduce 1, 0, 0 in here, and the problem reduces to these sets of equations. This then simplifies further to give us that the problem to be solved actually is the roots of this determinant. I've multiplied things out, so you can see here the first term is basically this one minus this times m2. Then you've got minus K23 here, and so on. If you then multiply out the determinant, so you've got this term multiplied by this term minus this times this, you'll end up with a quadratic expression in terms of omega squared. There will be an omega to the power 4, but it will be quadratic in omega squared. You can solve the roots for this quadratic equation, which will give you two values of omega squared for nodes 2 and 3. You can then determine the frequencies using this expression. Once you've got that, you can go back into the equation shown on the previous slide and determine the displacement, the eigenvector for each of the nodes from the expression here. Again, rather like the buckling example that I showed in the video on lecture 3, we cannot obtain absolute displacements. What we obtain here are relative displacements, in other words, the mode shapes. You'll find a more detailed description of this at the end of the video on lecture 3. Dynamic analysis can also be used for vibration problems. So, for example, this tuning fork could also be analyzed as a dynamic analysis, although you won't be able to very easily extract information like frequencies. But it can be analyzed, and also it can be applied to problems like the buckling section buckling problem that we're going to be looking at later in this tutorial. I did cover dynamic analysis in the video on lecture 3, although I tended to focus on explicit finite element methods. I rather jumped over this direct integration method that we're going to be using here. It was also used in tutorial 2 for transient heat analysis, so if you are interested, you might want to look back at that. For this dynamic analysis, we're going to be using this direct integration method, and for mechanical problems, this is based on the dynamic equations of motion shown here. So mass times acceleration plus damping times velocity plus stiffness times displacement is equal to applied loads. This would be the equilibrium conditions for a dynamic problem. We can use central difference equations to obtain velocities at time t in terms of previous displacements and forward displacements divided by a time step that we use in the analysis. And similarly, the same sort of equation could be expressed in terms of displacements at a full time step minus displacements at a full minus time step, divided in this case by 2 delta t. Velocities are obtained in a similar way, given here. So velocity at a forward half time step would be these displacements at t plus delta t minus these displacement at times t divided by the time step. And for a previous half time step, the velocities would be given by something very similar in terms of current time and previous time. Accelerations would be given by this relationship. So velocities at forward half time step minus velocities at a previous half time step divided by the time step, or feeding this into here and this into here, we can obtain this expression, which is accelerations in terms of displacements. In this case, we have the time step squared. For the dynamic equations of motion at any time t, given here, we can bring this relationship into here, and we can bring this relationship into here. You then end up with equation of motion in terms of previous information and displacements at a forward time step. So taking all of that and manipulating the equations, you will end up with this. And as I say, you have a prediction for forward displacements, t plus delta t, in terms of known information. So we know these displacements at a previous time step. These are the displacements at the current time step, at the current time. These are known applied loads. The time step, of course, we know we've set. And these stiffness, mass, and damping matrices are also known. We're assuming in this method that these are not changing during this time step. If you do have a geometric nonlinear problem, for example, where the stiffness is changing with displacements, then you have to use you have to use all of this in a Newton-Raphson type scheme. But we're assuming here that they're not dependent on displacement, and the mass and damping don't change either. So once you've got these displacements, you can then use that to compute accelerations, and you can use it to compute velocities. And they would be used in the next time step. So it's a quick overview of the method. On the next slide, I'll present the Newmark method, which does apply these techniques. The direct integration method I showed on the previous slide is used in Calculix, but it's used in a slightly different form. It's using the Newmark method, which actually is a variation of the Hughes or Hilbert-Hughes-Taylor method, HHT method. I'll quickly explain each of these. The Newmark method computes displacements in terms of previous displacements, velocities, and accelerations. The difference here is that the beta term here is introduced so that proportions of current acceleration and future acceleration are used in the calculation of the accelerations. In a similar way, the forward velocities are dependent on the current velocities, and the accelerations, which are split into two parts using this parameter gamma. So we have current accelerations and future accelerations. If we write the equations of motion at a forward time step, as shown here, then you can use the forward accelerations in here. So this is our way of getting the this term into this equation, forward displacements. Other information shown here is all known. And similarly, if we introduce this into here and then introduce this into here, meaning this whole set of terms, we end up with an expression here in terms of forward displacements, and we can solve for these forward displacements. So the essential difference to the previous slide using the finite difference equations is that we've introduced this beta and this gamma parameters to take different contributions of the acceleration from the current time step and the forward time step. This has certain properties concerning accuracy. The values of beta and gamma that you use influence the accuracy, but it also has certain damping properties. So high frequency terms that do occur in the accelerations can be damped using certain values of beta and gamma. Once you've solved for your displacements from the dynamic equations of motions, you can then retrieve the velocities at the forward time step and the accelerations at the forward time step. And of course, these become the velocities and acceleration at time t in your next time step. You'll find that if you use gamma equal to 1/2 and beta equal to 0, then these equations reduce to the same as the previous slide, the simple finite difference equations, central finite difference equations. Another common set of parameters are gamma equal to 1/2 and beta equal to a quarter. This gives a constant acceleration during the time interval t to delta t. If you use gamma equal to 1/2, you don't have any damping, and if you select gamma greater than 1/2, then you will start to get some damping in the solution. The actual method that's implemented in Calculix is this HHT method. It's essentially exactly the same, except now the equation of motions are formulated slightly different. We have an alpha parameter introduced in order to split up the velocities and the displacements. And this alpha also influences the time step, or the time interval. So t plus delta t actually becomes t plus this term here, so the time step is varying. This method gives better accuracy than the Newmark method. It is also possible to have damping. The value of alpha is selected to be between -1/3 and 0. The default in Calculix is -0.05. But once you've selected a value of alpha, you can then determine this gamma and beta values, which are the gamma and beta values used in the Newmark equations, and then essentially the Newmark method is used. So it's a very brief overview of these equations that and the method that's used within Calculix for direct integration of dynamic problems. This is the tuning fork example. I use in the book two examples, or two variations, a Model A and a Model B. The Model A is very quick to generate. It's basically just using cubes which are extended and repositioned and then joined together. It's a useful way of quickly determining prong length to get a certain frequency. But I'm going to be using in the following tutorial the Model B there shown there. It just gives an opportunity to show a few more CAD capabilities in FreeCAD for meshing. At the very bottom there is a analytical formula for fork frequency. It depends upon the length of the prongs, density of the material, stiffness of the material, and this A is the dimension here. It doesn't work very well, this formula, for this particular case because of this geometry here. The formula is based upon a built-in cantilever beam, so it would be sort of built in here, and then you can compute this length necessary to give you this frequency. You have to be careful there in that particular formula that's shown. You have to use these consistent units given here. So for example, length and this parameter A have to be in meters. This is the eigenvalue buckling analysis. I did go through this at the end of the video on lecture 3. I explained a bit about buckling. I explained the theory, and I also gave, I think, a useful example which should have helped to explain the calculations for eigenvalues and for eigenmodes for a simple buckling problem. I'll be using a more complicated example here using Calculix. Essentially though, the aim is to work out the roots or the eigenvalues of this set of equations, where this is the stiffness of the structure and this is the initial stress stiffness matrix, which was described in the video on lecture 3. In this particular case, lambda here are the eigenvalues. So these represent the scaling factors that are applied to the actual load of your structure to get the buckling loads. And finally, this is the example I will be using in the following tutorial, in the next parts of this tutorial. It's a simple thin-walled box beam section. It's built in at one end, completely fixed. It has a load at the other end here. Dimensions 500 long, 100 wide, 200 deep. And we'll just compute the buckling loads. Calculix will provide these eigenmodes, or so-called buckling factors. So for example, with this particular loading, the first eigenvalue is 20.6, which means the buckling load for the buckle to happen is the applied load, which I use 1 kilonewton multiplied by this 20.6. So 20.6 kilonewtons. That's a quick introduction. I'll move on in this tutorial now to use FreeCAD and Calculix for this frequency analysis. First of all, I'm going to create the CAD geometry for this tuning fork. I've started FreeCAD. I'm using version 20, as you can see here. I had troubles with version 19.3. There is a known bug for frequency analysis with that version, so I'm using version 20. As I say, it's the beta version, should become the standard version soon. If you need to use this version, you have to download it from the FreeCAD website. It is not the standard. As I say, it's the beta. Download the complete directory to your PC, and then you have to start the executable in the bin directory. So first of all, we create a new file. I'll use the Sketcher CAD workbench to do this. We specify the XY plane, and I'll first of all create the two arcs. Click on here, drag out, and then draw the first arc. I'm not worried about dimensions at the moment. We do the same for the second arc. We can set the dimensions later with other constraints. Can we stop with the right mouse key? I'll then use this option here for a polyline. We create, go over the point. When it changes color, it means it's kind of tied together. Come out in a straight line to any point actually down. When it is a straight line, you get this vertical constraint appear. So I'll click on here again and then back to this point. And then with the right mouse key to stop that. I'll do exactly the same for the lower point. And again, the right mouse key to stop the operation. I don't know if you noticed there, but if you get very close to the point, it will connect the two, and it has automatically put in the constraints for a tangent at these particular points. We've got the vertical constraints here. I'll connect these two with a parallel constraint. And we can start dimensioning things. So I'll use this constraint here to specify that between this point and this point we have 8 millimeters. And between this point and this point we have 16 millimeters. I'll specify that the length here from this point to here is 80 millimeters. Because of the constraint I introduced between these two, they both take, or both prongs as it were, take on the right length of 80 millimeters. I'll create part of the handle. Just start with some point here, move out, trying to keep the lines vertical, and then back to this position here. We could now use this trimming tool here to trim off these points. If you make a mistake, there is an undo option to correct things. So they're connected. We want to have, well, they are parallel connected. Not sure on that. Let's set the length here of between here and here of let's say 35. I think in the original it was 40. Let's say 35. It doesn't make much difference. And I'm going to create a handle, a little kind of grip at the end here using a circle. This is convenient for holding it. It's not really necessary for the frequency analysis or the eigenvalue frequency analysis, but it is convenient for a dynamic analysis I'm going to be doing. So I'm just going to create something here. Sorry, I didn't do that correctly. Let me repeat that. From here outwards. And then I'll specify the size of that with the circle constraint. We'll make it the radius, let's say 10. See how that looks. A bit large maybe. We'll make it 7.5. Okay, again, we'll use the trimming tool. Sorry, here's the trimming tool to trim that. Right mouse key to stop the operation. I'll draw over that and then can just simply delete it with the delete key. I need to make sure that this circle and also these two lines are really in the center. So I'm going to set a vertical distance between this point and this point, also between this point and this point of 2. So let me use this vertical distance constraint, which I haven't done properly, so I cancel that. I click these 2 points and then do the vertical constraint and put in 2 millimeters. And I'll do the same between here and here. 2 millimeters. And I will do between the center of this one and here, also in the vertical distance of 0. So that should be the structure complete. We'll exit that using this operation here to leave the sketch. We can go into the part workbench now and use the extrude operation with 4 millimeters. Each of these prongs is 4 by 4 in cross section, so we want to extrude this 4 millimeters. Apply. OK. So that's created a reasonable representation of this tuning fork with a prong length here of 80 millimeters. You could make this a bit more elegant, perhaps by going into this filleting operation, and you can get curvatures on these parts to make it look quite nice. But I'm going to leave it like that because some of the analyses I will be doing will be computationally a bit expensive. They will require some computer time. So I need a fairly coarse mesh, and I think I'd like to keep the geometry as simple as possible. I'll now go into the FEM workbench, set up an analysis container. So we've got our solver here. I'll just click onto the part. We've got the GMesh or the NetGen mesher. I'll try GMesh first, see what sort of a mesh that produces. Perhaps I'll use 2 millimeters. That allows me at least to have 2 elements through the thickness. We'll have a look what that creates. And that is actually quite a good mesh, I would say. It's fairly coarse, but as I say, some of the analysis I would like to do are rather expensive, so I'd like a reasonably coarse mesh for that reason. I'm going to say, okay, we'll use that for the analysis. So we can start defining a few boundary conditions and materials to do a frequency analysis. First of all, it's good to constrain it. I will fix the end. It's not absolutely essential for a linear eigenvalue frequency analysis, but this will block rigid body modes. So we'll fix the handle. Okay. And then I'll define a material. Now I'm going to use steel. That's in here under Calculix steel. Here. Density is 7,900 kilograms per meter cube. These are in the units, FreeCAD units, which will be converted when we write out the data set for the analysis with Calculix. So we'll say OK. And that's all I need to do for a eigenvalue frequency analysis. If I double click on here, I don't need any displacements or forces or loading. Double click on here. I'll select the directory. Well, let me cancel there first. I wanted to just check one thing down here. It's quite good if we use the split option for the output. So it is active. The frequency information is also specified here. This is the range for frequencies, the highest limit, the lowest limit, and 10 modes. We will see this again on the input data set in a moment. That's fine then. So I'll double click on here. I'm going to save to a directory I have for this particular analysis. I'll write out the data set. Now we don't have to look into it, we could do a run straight away, but I'm going to open this just to show you. So all of the inputs have been split off. For example, this is the nodal information. Here are the constraints information. They're in these include files, and you will find these in the directory in here. Here's my material data. I only need the modulus and Poisson's ratio. We don't need any density for doing a linear eigenvalue frequency analysis. It's a static analysis. So I made a slight mistake there. I should have activated the frequency here. I will close this, activate that, write the output file, edit. So the same applies, it has included the density here. Of course, that's wrong what I just said. You do definitely need the masses for doing a linear eigenvalue frequency analysis. So this density is very important. 7.9 e to the minus 9. You don't need the density when you're doing an eigenvalue buckling analysis. It's a frequency within this analysis step. So the analysis step is down here to this point. We're doing a frequency analysis. We're selecting 10 modes. I could increase this to 20 or 30, but 10 for the first 10 eigenmodes and eigenvalues between 0 and this upper frequency. So it will be the 10 lowest that we'll collect or determine. That's fine. I will close this. There was no changes made. We'll run it. It will go fairly quickly, but I will stop the video for a moment while it's running. So total time 25 seconds. We can look at the results now. We'll close this, and what you'll see here are the 10 eigenmodes for this particular problem. There will be no rigid body modes because we've constrained it. So for example, if we double click on there, we can look at the displacements, and you will get some idea of magnitude of displacements, but keep in mind these are not, and you can see by the sizes here, these are not physical displacements. They are relative magnitudes. It's all we can get from an eigenvalue frequency analysis. And these create a bit of a problem, because if we look into the deformations, it's kind of crazy. Unfortunately, there is still a bit of a problem here, but this is to say that is the mode. It's bending upwards here, and it will go backwards. We'll see this better in a moment in the CGX post-processor. We close that. I'll select another one, maybe the fourth. I think the fourth is the one that's most of interest for us, because this is the mode that corresponds to how a tuning fork should vibrate. We'll click on that, and again it's, well, I can probably, can I reduce this? No, I can't. Okay, it's a bit better. So this is the vibration mode of a standard tuning fork, where these two prongs move symmetric about this center line. We'll look at these, as I say, in a second in the CGX post-processor. In this DAT file, we can open this. Now, these are the omega squared eigenvalues. These are the omega square rooted, or the omega values, and here is the frequency. So this first mode that I showed you is vibrating at 185 Hertz. The fourth mode, where the prongs are moving opposite to each other in the vibration mode of a tuning fork, is moving at 421 Hertz. Let's take a quick look in the results file using the CGX Calculix post-processor. We have to open this FRD file. This is the one that's just been created. It's loading up the results. I can select, well, here are the 10 modes. I'll select the fourth one, displacements, and the entity is the Y direction. And if we go under animate, start, you can see this mode. We can have a look at that first mode again, just out of interest. Displacement, and then you have to collect the D2 for the Y direction, and then animate start. So you can see this vibration mode. Now these first three modes would not happen in practice really, because we tend to strike the tuning fork from underneath, and then it starts this mode 4 that I just showed you. These modes are not likely to develop. If they did develop, what would happen is, because you've got this movement taking place here and you're holding it, these modes would be quickly damped. Whereas this mode 4, where one prong comes this way and the other prong comes this way, you've got no movement along this center. So if you're holding it, you're not actually damping the system at all. Maybe just from interest, we can have a look at another mode. I don't know, let's have a look at this sixth one, see what it is. I'm not sure. I have to do T2, and then we go under animate to start it. Okay. Again, this is a very unlikely mode to take place, considering the way it would be hit. And if it did take place, because you'd be holding it here, it would quickly damp. So that's essentially an eigenvalue frequency analysis. The important point, as I was trying to show in here, is here is the information that you're interested in. These are the modes. These are the eigenvalues. And here are the frequencies. And these frequencies are determined from this information. We can close this up, and I think it's interesting. I can show you how we can do a dynamic analysis of this particular problem. I'll delete all the results, and we'll bring up the model again, center it. With the eigenvalue frequency analysis, we don't actually have to apply any boundary conditions or any loading to the structure. The eigenmodes are determined from this instability criterion, which correspond to particular deformation modes. I did, in the analysis, the linear eigenvalue analysis, I did impose some constraints. They're shown here. But these were only to suppress rigid body motions or eigenmodes associated with rigid body motions. If we're doing a dynamic analysis of this problem, however, we do have to impose some kind of a loading to deform the structure. I'm going to impose some forces. This direction here and this direction here could be either inward or outward, it doesn't really matter, but these forces will then create some deformation, and then you will get some oscillation started for this each of these prongs. And these oscillations we'll try and compare with or the frequency from these oscillations we'll try and compare with what we got from the linear eigenvalue analysis. I do have boundary conditions again to hold the structure, so I leave those as they were before. I'll add these forces. We're selected here. I'm going to use just 1 Newton. The direction is obviously wrong, so I have to click on this direction flag and then some entity which is in the direction that I would like to have these forces. So I've clicked that. So that's now correct. If it was in the wrong direction, I could reverse. So we'll say OK. And then for the other end, we do exactly the same. Again, I have to define the direction. I need to reverse those, so that would be fine. This will create deformations rather like the prong when it's oscillating. Each of these will be moving opposite to each other, and this center will not be moving. The dynamic analysis is actually rather interesting for other load cases to see how things develop. So for example, it's quite interesting to ignore this one and just leave one load here, perhaps moving in the opposite direction, right? So replicating what would happen when you really strike one of these prongs, which is to strike it somewhere here. You'll find that this will start oscillating. You'll get some bending of this, and it takes a certain amount of time before this prong starts moving symmetrically with this one, and you get no deformation there. That's quite a nice exercise for dynamic analysis, and something you might want to try on your own, as it were. Anyway, that's the problem we're going to analyze. It's complete, actually. I don't need to do anything else. We're only applying a very small load here. If you noticed, it's only 1 Newton, so the deformations will be small. I could use a larger load or a larger force. That would increase the amplitude of the oscillations, but the frequency of the oscillations is just dependent upon the geometry, the stiffness, so that means the Young's modulus of the material, and the mass of the material. So I'm just going to use Calculix steel as before, and these forces will be sufficient. We'll just check in here under the solver that we're using the split option. It makes the when we're looking at the data sets, it makes life a little easier. And we'll double click on there to start the analysis. I'm going to use the directory I've been using for storing results. We're going to do a static analysis, but I'm going to change things. So we write the output file, we now edit it. Now down here I have to specify the density. It's been cut. It is in the database, but specifying static means we don't need the density, and so it's not output to the Calculix file. 7.9 e to the minus 09. And down here we've got step, so our analysis step is down here. Currently down to here. Currently it has static, but I'm going to change that to dynamic, comma direct. And in here I will use time steps. So this will be the time step in the direct integration scheme. And we're going to do this for a total time of 0.05. It would be nice to do this for 1 full second, for example, but that takes quite a lot of computing time, and there will be an enormous amount of generated results files, especially with this time step. So I'm only analyzing for 0.05 of a second. This then should produce 100 points of information for the behavior of this vibrating prong system. So those are the only changes. We'll save it and run the analysis. Now this will take some time, several minutes, so I'm going to just stop the video and come back to it when it's complete. So the analysis has completed successfully, just over 5.5 minutes of computing time. We can have a look at the results, but they're not really very interesting here. For example, you could click on one of these and have a look at the displacements. These are now, contrary to the linear eigenvalue analysis, these are correct displacements that we're seeing here, albeit for the loading we've applied, and usually we don't really know the loading, so we can't take too much notice of these displacements. This would be 0.07 millimeters, for example. We could also look at stresses created. Main stresses are in here. But the more useful information is in the, or can be visualized from the Calculix C CGX post processor. So I'm just going to close this, reduce this, and go into that directory and open this FRD file. Now this is the post processor for Calculix. I explained around the middle of the lecture, lecture 7 I think it was, how you can install this, at least on Windows. We'll double click on that. This will take a little time to load up the file. There has to be 100 states to be loaded up. So we'll just wait for that. And here we see the structure. We can look at, well, the usual way. We would come in here and toggle data set to start to set up a sequence of the stored time steps. I will select the first one to start it, displacements. I come back into that again, selecting here all. Well, no, I'll select D2. This is the displacement in the vertical direction for this tuning fork. And we can see here contours of these displacements. We can create a graph, time history graph. I'll select 2 nodes, better we shift that so we can see the information here. We'll select 1 node here and 1 node here. Right mouse key to stop that. And these then are our displacements for the 2 nodes oscillating. We can see we've got, let me just count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 oscillations over a time of 0.05 seconds. That means it would be, in terms of seconds, it would be 360 Hertz. So the 360 is a rather below the 420 we predicted from linear eigenvalue analysis, frequency analysis. The main reason for this is we haven't used enough time steps in the direct integration process. There's also another problem that we can see, is that the amplitudes are gradually reducing. This can be due to 2 things. There is a parameter alpha that's used in the direct integration. It's linked to the Newmark method, for example. This is a damping factor for numerical stability. The default is 0.05. You will find this in the Calculix manual. We can set that to be 0, and if you do that, usually you will find there being no decay in the oscillations. But in this case, the main problem is that we haven't selected enough time steps for this integration. So I'm going to repeat that and change and have more time steps and redo the analysis. We'll close this, and open the file again. We'll delete all those results, and this result here has no meaning for us. And then under the solver, we'll come in here again, write out the input file again. Of course, I need to change it to the directory so I can store my results in a place I can easily find. We'll write out the input file, edit it. I have to do the same thing again. Density 7.9 e to the minus 0.9, and here we will have dynamic direct integration, and we'll put in here 0.1231, 0.05. Now this is a much smaller time step. Previously it was 0.0005, giving us 100 points. Now we have 0.0001 giving us 500 points for the complete integration process. We've got our time step. Another thing we have to enter in here is, in this case, increments equal some number over 500. The default is that this is set to 100, so after 100 time steps it would have stopped the analysis. We now need to increase this default to 1000. So those are the only changes. We'll save this and run it. Now this will take, I have an error, edit input. What did I, 7.9 e to the minus, there's a typo there, minus 09. Okay, the rest is correct. So we'll save that and run it. Okay, now it is running. I'm going to stop the video again because this takes 20 or 30 minutes to run, and then we'll have a look at those results. The analysis this time has taken 25 minutes. You can see it here, and the analysis has been successful. There are all the results in here, so we could look at results here if we wanted to, but again it's more meaningful to look at these in the Calculix CGX post-processor. So I'll reduce this and we'll look at the results here, opening this FRD file. This will also take a bit of time to load all these data sets, so I'll just stop the video for a moment. So the 500 states or points have been loaded. We can follow the normal procedure, and we can toggle data set sequence, select the first state, displacement I'm going to take, and down here I have to then select the type of displacement. I'll use D2 again for the Y direction, and then we'll produce a graph of a couple of points. Move this across so that we can just check. So here's the first point, here's the second point on the two arms, with the right mouse key to stop that. And here now we see the much cleaner view of the oscillations, I would say. As you can see, there's no decaying in the amplitude. In this time indicates a much better solution. And let's just count here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So 21 peaks instead of 18 now. 21 over this time would be 420 Hertz. So that now agrees very closely with the result we had for the eigenvalue frequency analysis. I hope it's clear. There's a very different solution method being used here to simulate this dynamic behavior, and very good results, or a good comparison. You could compare these with the analytical formula I gave for a prong at the beginning, but you won't find such a good comparison there. I think the main reason is because it's using the formula is really for a built-in cantilever, whereas we do have this quite complex curved geometry which the prongs are attached to. So it's a slightly unusual application for dynamic analysis, but I think it gives you some feeling how this works, and it's quite a critical critical analysis or problem, because we do have a high frequency behavior, and we can see that the number of peaks do agree well to there's a kind of validation to the linear eigenvalue frequency analysis. I'm going to move on and just show you how we do rather similar analyses for buckling, and that'll be in the next part of this tutorial. So I'm going to do a eigenvalue buckling analysis. I'll create a thin-walled channel section. It'll be 500 long by 200 deep by 100 wide, which I'll fix at one end and load at the other end. And then we'll do this buckling analysis. One quick way, there are several ways you could define this section, but one quick way is to, under part, use the cube option to create the overall dimensions that you want for this section. So it's 500 long by width 100 and a height of 200. We can center that. So that's the overall dimensions. Then under the draft workbench, we can use this face binder option to create faces for the channel section. So in that case, I want this one, then I have to this one, I'll add them, and then I'll rotate around to get the other two, this one and this one, add them, and click OK. Now if I delete the cube, sometimes this message can be dangerous, but in this case it's fine. We'll delete this, and what we're left with now, I'll try and just rotate this around, you can see the channel section. I'll start the FEM workbench. We'll add an analysis container. I'll fix this end here using the constraint option. I'm holding down the control key, pressing on these, and then we'll say add and OK. So that end is completely fixed. And in the other end, I'm going to apply a load or a force using this icon here. Click on the entity, add. It's in the wrong direction, so we use the reverse option here. And it hasn't quite done what I expected, so we'll use this entity in order to align the direction we want. So that's fine, and I'm going to apply a load of 1 kilonewton, so 1000 Newton. Okay, so that's the loading and the constraint. We have to define steel. I'm going to use Calculix steel. Okay, in the materials, most of that we didn't need, but we do need the modulus and the Poisson's ratio. Next, we have to define the thickness of the sheets. That's done here. One at a time. I've done this time, and I'm going to define them to be just 2 millimeters thick, so thin-walled section. Okay, and of course the last thing we have to do is to mesh this. So I'm going to click on that. We can use a G-mesher. For example, if I use 10 millimeters and 10 millimeters here, apply, we get a mesh. It would be reasonable to use. It doesn't look particularly elegant, so I'd like to show something a little bit different here. If we cancel that mesh And under the options for GMesh, we can activate a different mesher in here. So there's a range of meshers possible, but if we select the Del Quad mesher and now try to mesh it, we get a more sort of structured mesh, but these are again triangles. So I should cancel that. And once more, under these options, you will see down here a recombine option. So I put true. We now can apply our mesh, and in this case, all those triangles will be recombined to give us quads, and we have quite a nice quad mesh for this structure. Calculix has no problems to analyze these elements. So we'll say OK. That is everything defined now. We can go ahead and do the analysis. As usual, it's quite good to specify a directory, and I've prepared one where we can store the results files. Otherwise, you can use the temporary directory, but if you wanted to look into that for any reason, then you've got to search through these temporary directories. Here, this one, I know where it is. If you're using version 20 and above, I've seen that there is a buckling option in here which you would activate. I'm using version 19 here. It's not available, so I'm going to use the static and modify things. So write the input file, edit the input file, and in here, down here, what we have to change, this has to be replaced with buckle. And on the next line, we have to enter in the number of eigenvalues or eigenmodes that we want to extract. So those are the only changes. We'll save this. Okay, and we'll run that. Now this shouldn't take too long, but I will just stop the video for a moment. So 24 seconds for the analysis, calculates done without error. That's fine. We can close this now, and what we will see here are the 10 eigenmodes for the analysis, plus this results file. Now I'll look at this one first. What we're seeing here, these are the eigenmodes. Sorry, the eigenvalues. Here we have a value of 20, so it's 0.2 raised to the power 2, so it's 20. And that means that the applied load, which was 1 kilonewton, has to be multiplied by 20, giving us 20 kilonewtons. And 20 kilonewtons would be the load causing this particular buckling to occur. The next one's occurring at 26.99 kilonewtons, and the last one is at 89 kilonewtons. That's the only useful information in this file. We'll have a look at the first one. I'll double click on that. Displacement magnitude. We've got values for displacements, and if I was to come in here, we would have values for stresses. But these are not real displacements. They are all relative displacements to give us the eigenmodes. Similarly, looking at the stresses, they correspond to these displacements, but they are not meaningful stresses. So we'll just look at the shape. I'll apply, well, we need to get a better view here. So we can see it deforming slightly. It will be better to increase the scale here. And here you can see the buckling has taken shape. It's moving out this way, and because of that we get this deformation at the top, moving out again. We'll have a look at the next one, see what that does, and we can see this alternative buckling mode. What was it? The first mode happens at something like 20 kilonewtons, and this was something like 26 kilonewtons. Let's have a look at one of the latter ones. Yeah, that's quite a nice one. You can see this wave occurring here, and there's also a buckling occurring in this face. You can also look at these results in the FRD file saved to that buckling directory. You look at that with the CGX post-processor from Calculix. The plots are maybe a little bit better, maybe a little bit more informative, but essentially that's the process for doing an eigenvalue analysis. The main disadvantage of this is that you don't usually know which of these modes is stable or unstable. So it could have been, I don't think it would be the case in this particular study, but for example, if we look at this one, it could have been that this wouldn't cause an unstable problem. This mode could develop, and then some other buckling mode somewhere else is what would cause the structure to collapse. But looking at this, this is likely to be a critical buckling mode in this particular case. If you really did want to study how a structure collapses, you could use direct integration methods. So we would do a similar approach using the same sort of options as the dynamic integration or direct integration in the frequency problem. You would apply displacements here, which would push down, I don't know, probably 50 millimeters maybe would be sufficient. And you'd use a direct integration keyword. You'd have to have a certain amount of time. You wouldn't want to do this in 1 or 2 seconds because you will have inertia effects. You would probably want to analyze this over a slightly longer time, maybe 5 or 10 seconds. You will need a certain number of time steps to make sure you can properly follow or accurately follow the deformation process, and you don't have too many problems with convergence. And that will tell you how these modes develop and which mode is likely to be a critical one for the collapse. I have done these things with a reasonable amount of success with Calculix, but it does prove to be a bit challenging. The main problem is that as you get these buckling modes develop, the stiffness matrix tends towards 0, and convergence does tend to become a bit of a problem. Certainly these sort of things are much easier handled with a truly explicit finite element code like PAMCrash or LS-DYNA or Radius. Radius would be another one, or Abacus Explicit. So I think that's all I wanted to cover for these buckling problems. The next tutorial I want to do will be something quite different, using OpenFOAM for dynamic computational fluid dynamics.